Now we will go through another agenda today. It's a very important subheading of matrices. Many years gate have asked questions on this particular thing. When you refer the last 10-15 years papers which is provided to you in your question banks, you will find a lot of things happening there in terms of this topic. The agenda for today is called as question based on or understanding eigenvalues and eigenvectors. We have seen this topic in our earlier days of engineering. First year and second year of engineering, we have seen when we were studying about matrices about eigenvalues and eigenvectors. First, let us understand what are eigenvalues and what are eigenvectors. Right? Let's say there is a matrix A. Right? There is a matrix A. It's a square matrix. Right? Of order n. Of order n. That means it is n cross n. We can form a matrix which is of the form A minus lambda I, where I is the identity matrix of the order n again. Right? This will be of the order n again. Right? It's a unit matrix. And I is the unit matrix or the identity matrix of this kind. Right? And if I say that the determinant of this particular A minus lambda I A is equal to 0, this is called as the characteristic equation. This is called as the characteristic equation of A. This is called as the characteristic equation of A. Getting my point? Now, roots of this equation. Also, roots of this equation are called as eigenvalues or latent values or you can sometimes refer it as latent roots or characteristic roots. So if any of the three has been asked in the paper, you have to understand the same thing only of the matrix A of the matrix A. Now it's very simple to understand mathematically, right? I said there is a matrix A of the order n. You have to find A minus lambda in, where I is the unit matrix. If you find a determinant and equate it to 0, this forms a characteristic equation of A. This forms the characteristic equation of A, and the roots of this equation are called as the eigenvalues of latent roots or characteristic roots of matrix A. Getting my point? Right? Now, if you talk about eigenvectors, we'll take it later on. This is something called as eigenvalues. Clear? There, with eigenvalues, we will develop eigenvectors, which will be directing towards these values. The vectors which are directing towards these values are called as eigenvectors. Now, in a layman's language, as I told you earlier also, these are system parameters, right? The value of lambda or eigenvalues which we will be getting are system parameters. I can define a system on the basis of eigenvalues. For example, I say that the eigenvalue for this system is 4, 3 and 5. So that means that a system has eigenvalues 4, 3, 5 will be unique across the world wherever based on this particular thing you can always say, right? For example, this is sort of an ingredient when you make a dish, right? So you say 2 teaspoon of this, 5 teaspoons of this, 5 kgs of this, so this is a unique recipe which a person in X place is making or a person in Y place is making. He will be able to develop the same kind of recipe because the ingredients are same. So that is how these are system parameters. If you want to design a system and if you say these are the eigenvalues, right? So anywhere if you design a system, if you know the eigenvalues corresponding to those eigenvalues, the same type of system can be developed. Is it very clear to you now what is the physical interpretation of this particular thing, right? Now similarly the vector form from these values, substituting lambda values back to the equation, right? If you talk about what are eigenvectors, let me write it down here itself. What are eigenvectors? So if you say eigenvectors, you can you can easily say this, that the vectors corresponding to these eigen values, or you can say values of lambda are called as eigenvectors, right? It seems to be some absurd thing, but if you solve the questions, you will be very clear what are eigenvalues and eigenvectors, right? So before going to the question types, let us talk about the properties of eigenvalues, right? But in case, let's say, let us solve one small example to make things very clear to you before going to the properties. In fact, let us say you find the eigenvalues. It's saying find eigenvalues of the matrix A is given as 4 minus 2 minus 2 1, right? This was basically a question from GATE 2004 paper, and I'll give you the options. Options are 1 and 4. Second option was minus 1 and 2. Third option was 0 and 5. And fourth option were 4 and 3. Right? So these were the options which were given to us. Right? So let's understand how to solve this methodologically. Right? Methodologically, if you say the first, I will find A minus lambda I. So this will come out to be A, that is 4 minus 2 minus 2 1 minus lambda times I will be of the order of this only, so 2 cross 2. So if you solve this, this will come out to be 4 minus lambda I minus 2 minus 2, and this will become 1 minus lambda. And this I you can omit, it is not basically required, and this is the A minus lambda I matrix. Right? Now what I said was determinant of A minus lambda I should be equal to 0. So 4 minus lambda minus 2 minus 2 1 minus lambda, determinant should be equal to 0. Right? So if I take the determinant, we know how to find out the determinant. So it is 4 minus lambda into 1 minus lambda, cross minus of plus 4, that means it is minus 4 only, is equals to 0. Right? So if you solve this, this becomes 4 minus lambda minus 4 lambda plus lambda square minus 4 is equals to 0, or you can say 4 and minus 4 gets cancels out, so this becomes minus 5 lambda plus lambda square is equals to 0. Or you can also rearrange it something like lambda square minus 5 lambda equal to 0, or so lambda is equal to 0 and 5. Right? So these are your eigen values, 0 and 5. Clear? So this is how you find out the eigen values of this equation. So the answer will become very simply 0 and 5. Right? Clear? How to find out the eigen values? Right? Okay. Now let us talk about properties. Before going to the more, we'll solve more questions on this and we'll see how to find out the eigenvectors also. But before going to that, let us find out some properties of eigenvalues. Now these properties can also be called as shortcuts. I will tell you the question which we have just solved could be done in 5 seconds. Now you'll be wondering how 5 seconds. I'll tell you how 5 seconds. Right. First, let us go through properties and we will discuss about this particular thing. Right. Number one property, it says that sum of all eigenvalues, sum of all eigenvalues is nothing but is equal to the sum of elements of principal diagonal. Principal diagonal elements, you know, right? If you sum all the principal diagonal elements, which will be equal to the sum of the eigenvalues, right? Okay, I'll tell you how to use this. Second, the product of eigenvalues, the product of eigenvalues will be equal to the determinant of matrix A, determinant of matrix A of matrix whatever given, not A, in fact you can say whatever matrix is given to you, the determinant of that particular matrix, right? Third property which will say, now if you talk about transpose of a matrix, then eigenvalues don't change. See, eigenvalue I told is a system parameter. Now when you take the transpose, you are just shifting the rows to the columns, you are just shifting the rows to the columns, but if you find out the overall eigenvalues, they won't change. So for any square matrix, any square matrix A and its transpose, so any square matrix A and its transpose AT will have the same eigenvalues. Clear? Let's see how we will use this property in fact. Now talking about fourth property, the next property says, you can say the eigenvalues of a triangular matrix, eigenvalues of a triangular matrix is nothing but the diagonal elements of that matrix is equal to the diagonal elements of the matrix directly, whether it is an upper triangular, whether it is a lower triangular. Directly you can say that the eigenvalues is nothing but the diagonal elements, right? Now in this fashion only, if I take one more corollary of this, if I say that eigenvalues of a diagonal matrix, what is the diagonal matrix? Which is only the diagonal elements. Diagonal matrix is nothing but, now it is very quite evident, it's just the diagonal elements of this, right? So you can always say that again the diagonal elements of that matrix, right? So this is very simple. Similarly, we can form one more property which says that if lambda is the eigen value of A, of matrix A, then 1 by lambda will be the eigenvalue of A inverse. So sometimes question are asked, you are given the matrix A, right, and he is asking you to find the eigenvalue of A inverse. So don't find A inverse first, directly, because A inverse will require a lot of effort. You have to find cofactors, you have to find minors, you have to find adjoint of A, then A inverse, and then you find out the eigenvalues of it. So it is better to find out lambda of A and inverse it. That will become the lambda of A inverse. Very simply, right? Then you can also generalize this thing. One more property which you can say is, if similarly if you expand this, if lambda 1, lambda 2, and so on up to, let's say, lambda n are eigenvalues of A, right? These are eigenvalues of, let's say, matrix A. Then then eigenvalues of A to the power P will be lambda 1 raised to P, lambda 2 raised to P, and so on up to lambda n raised to P, where P is a positive integer, where P be a positive integer, right? For example, is saying that the eigenvalues of A are given to you 1, 2, 3, and eigenvalue of A square has been asked. Very simply, let's say if there is a question where you are saying that if eigenvalues of A matrix are 2, 3, and 4, then find the eigenvalues of A cube. So don't find A cube first, right? You can very simply say that the eigenvalues of A cube will be 2 cube, comma 3 cube, comma 4 cube. Right? This will be 8, 27, and 64 respectively. Clear? This is how you can find out the eigenvalues, right? Now let us solve some more question based on this property so that we understand this. Okay, now I was just talking about the previous question which we solved. The matrix we wanted to find you find the eigenvalues. I'm repeating that question of the matrix was 4, minus 2, minus 2, 1, and I'll tell you the options given to were 1 and 4, second was minus 1 and 2, third was 0 and 5, and fourth was 4 and 3. Right? Now let us solve this. We know the method A minus lambda I and all those types of stuff, but let us solve it through options. You want the eigenvalues. Now you know that the diagonal elements, what are the diagonal elements? 4 and 1, right? The sum of the diagonal elements should be the sum of diagonal elements should be equal to the sum of eigenvalues. So the sum should be 5, right? Now in this option, is it 5? Yes, so this could be a possibility. Is this 5? No, so this is rejected. Is this 5? Sum? Yes, right, possible. Is this 5? No, so this is rejected. This can be a possible case and this can be a possible. Only two possible cases you got, right? Okay. Another property which we know is the determinant value. The product of the eigenvalues should give the determinant. So what is the determinant of this value? 4 2s are 8 minus, sorry, 4 1s are 4 minus 4, which will be 0. So the product should be 0. In this case, is it 0? No, the product is 4. In this case, is it 0? Yes. So that's your answer. Getting my point? With only two properties we use, you are able to get the answer in very less time. Clear? Right? Let us take another example. I take you another example. This is GATE 2003. The previous question was GATE 2004. This was GATE 2004. Again, you have to find the eigenvalues. Eigenvalues of 4114, right? So these are the things you have to find, right? Okay, options, I'll give you the options because we may use option 3 minus 3, minus 3 and minus 5, 3 and 5, and 5 and 0. Okay, so with options we will say what is the sum of eigenvalues is nothing but, I'm just writing it down for your convenience, but you can do it in your mind only. Sum of eigenvalue is nothing but sum of diagonal elements, in fact principal diagonal elements. Okay, so that is equal to 4 plus 4, that is 8. How many options ruled out? How many options ruled out? All the options ruled out. Only one option you can left out. This ruled out, this ruled out. That is the only option you get. Finish. Right? Very easy. Okay. So we have understood how to find out the eigenvalues, and we have seen how we will utilize the properties also. Let us solve a couple of questions which is based on solving of eigenvectors. Let's say question is given to you, which one of the following, or which of the following is the eigenvector of the matrix A is equals to 2 2 1 3. Right? We are asking which of the following is the eigenvector of the matrix A is equal to 2 2 1 3. Right? So before going to the eigenvectors, we will have to find the eigenvalues. Okay, I'll give you the options also, in fact, because which of the following it has been asked. So this is also a GATE question of 2010. This came in 2010. GATE 2010. Very similar sort of questions are asked in every year. So if you practice that is why it is recommended for you to practice the last 10 years papers. See, why IES Academy gives you this is because you have a question bank. You might be feeling why this question bank is given to us. Right? This question bank is given to you very simply because you practice. If this is my experience of so many years of teaching so many students, that if you at least solve the questions, every now and then if you solve questions, then definitely you will not find any difficulty in a GATE paper. I guarantee you 50 to 70 marks of question, 50 to 60 marks, in fact 50 to 60 marks of question you will see are very much similar to what GATE has asked in the previous year. Not exactly same, but similar I'm asking. Okay, so these are the options given to you. Right, so let us solve this problem. So first we will have to find out the eigen values. So first we will have to find out the eigen values. Right, so the matrix A, let us make the system parameters. Directly you can find out if you're using a property. I know that summation should be 4, sorry, summation should be 5, and the determinant should be 6 minus 4, 6 minus 2, that is 4. So determinant product of the eigenvalues, you can say lambda 1 plus lambda 2 should be equal to 5, and lambda 1 into lambda 2 should be equal to 4. Right, so if you can directly find out, the answer would be 1 and 4. See, there are two equation to unknowns, you can easily find out. Or you can also say, you can form the equation A minus lambda I, and determinant should be equal to 0. Any of the method. This is shortcut, this is via property, this is via property, and this is via method. So you'll find that lambda 1 is equals to 1 and lambda 2 is equals to 4. Now these are the eigenvalues. This is the half part of the question now. Now we want eigenvectors corresponding to, and we have to check that which of the following is giving you the eigenvector. So let us first check it corresponding to, let's say corresponding to lambda 1. Let us say, let us put lambda is equals to 1, or lambda 1, that is 1. So if I substitute in our matrix format, so it will become 1 2 1 2. Right, actually if I say, let us go back to a step, and we'll say that what is A minus lambda I? Matrix A minus lambda I will look like 2 minus lambda 1 2 and 3 minus lambda, isn't it? And what we are trying to do is, that we are saying that this is A minus lambda xi, this has become a characteristic matrix into x should be equal to 0. This we are trying to do, and this x will give you the matrix, right? So when we put lambda is equals to lambda 1 is equals to 1, so what we'll be getting is 1 2 1 2 of x1 x2, there are two variables, should be equal to 0 0, right? So when you solve this, when you solve this, what you are going to get is x1 row column, right? Minus 2x2 is equal to 0, plus 2x2 is equal to 0, and similarly x1 plus 2x2 equal to 0. The same equations you will be getting, right? So if you say that the ratio, the solution is x1 equal to minus 2x2, or x1 x2 is equals to minus 2 1, right? Solving any of the equation, you will get this x1 x2 is minus 2 1. Is it available in the options? No, we don't have this in the option. Is it? Yes, it is. See, it is not necessary that x1 x2 is minus 2 1. You can also say that, or it is 2 and minus 1. What is the difference if I say, you can say minus x1 is equal to 2x2, isn't it? So you can also say that it is 2 and minus 1, which is option number, which is available in option number A. It's available in option number A. So hence your answer will become option A. So option A is the corresponding eigenvector. Clear? So this is how you can find out on based on eigenvectors, right? So understood how we will solve question based on eigenvalues and eigenvectors. Now many of the question has been asked in gate papers. You can now go to your books, your workbooks, and you can easily find out how to solve questions on eigenvalues and eigenvectors, right? One last topic on matrices we also discuss. Sometimes very rarely the question has been asked, but still, as because that is in our syllabus, we will discuss that particular thing, and that is called as Cayley-Hamilton theorem. Let us discuss that portion also. That is name of the scientist, basically Cayley-Hamilton theorem. Now what is Cayley-Hamilton theorem? Let us understand this thing. What is the statement, or what does Cayley-Hamilton actually observed? What they saw was every square matrix satisfies its own characteristics equation. Now what do I mean by this particular thing is very simple. For example, if I say that, let us take an example so that it becomes very clear to you, right? Now this example I am taking from a gate paper again of 2007. What is the question saying is, if A is equals to minus 3 2 minus 1 0, then A satisfy, then A satisfies. Option A was A plus 3i plus 2a inverse equal to 0. B option, a square plus 2a plus 2i is equals to 0. Or third option, a minus I into a plus 2i is equals to 0. And the fourth option was e raised to a is equal to 0. right? So these were the four options which were given to you. So using Cayley-Hamilton theorem, we can always say, using Cayley-Hamilton theorem, we can always say that the matrix will solve the, you will see now here is nowhere mentioned that you have to use Cayley-Hamilton theorem. This will come through practice, that a Cayley-Hamilton theorem can be a very good bet for you. One way could be you find out a square or a inverse and you substitute in any of the equation and you can get the relation which of the following is true. But if you can observe this particular thing, wherever a inverse is there, you normally, and when the higher powers is there, normally try to use Cayley-Hamilton theorem. Once give it a shot, right? So using, you can say, initially first find out the characteristic equation, then we'll use characteristic equation. So characteristic equation of A is A minus lambda I should be equal to 0. So if you substitute this, it will become minus 3 minus lambda 2 minus 1 0 minus lambda, determinant should be equal to 0, right? So this is the characteristic equation. If you start solving this, you will get minus 3 minus lambda into minus lambda plus 2 is equal to 0. So which says that lambda square plus 3 lambda plus 2 is equal to 0. Now using Cayley-Hamilton theorem, you can say that lambda will satisfy A. You know, the matrix, square matrix will satisfy its characteristic equation. So we can also say that A square plus 3A plus 2 will always be equal to 0. You can say it is I because it has to be in a matrix format. So 2 means 2I. A unit matrix can be added. Can you see this thing in the options? Option B seems to be very much near to this. Not exactly this. It is A square plus 3A, right? Now if you solve the C option, it is making A square into plus something A, but it is not the same. Fourth option, if you say, again exponential of A will not be good. But if you see, if I multiply equation, let's say 1 by A inverse, what will it form? Try to understand. See, if I say this is A square into A inverse plus 3A into A inverse plus 2A inverse into I is equals to 0. So if you simplify, this will become A plus 3I, A into A inverse is I, plus 2A inverse is equals to 0. Can you see this somewhere? Yes, it's in the option number A. So you can say your answer will become option A. That's your answer. Clear? So this is how you can use Cayley-Hamilton theorem and get your answers in a very less amount of time. Right? So you can find out in numerous types of question based on this particular thing and get the answers for different points. Right?